Professor Paul Roberts, who's going to talk about coupling in the early solar macros. He's promised to talk quite quietly, so as not to disturb you sending your emails.
To connect to
Thank you very much. Well, this is kind of light relief for you from all this heavy astrophysics. And it's a topic I've been working on this last year quite a lot with Jonathan Arno. We were invited to write a review article, and this review article became less and less of a review and more of an original paper. So it was, in the end, not very satisfactory as a review. I mean, I know how to write reviews. You quote everybody, references to everybody you think of, and then you've written a satisfactory review. But actually, the topic is one that has really developed rapidly over the last few years. And I don't think I'll be able to get onto all the reasons why this is true, but one of them comes up fairly soon. Let me see. That's the one, isn't it? Yeah. So, see, the astrophysical background, you may want to get some clue about what the inside of the Earth is like, and it's not that. You see, the core of the Earth is not that. It's more like this. So I'd like to just remind you about the structure of the interior of the Earth. We have here, most of it's labelled. It appears that the Earth has been cooling over geological time, and recently, the last billion years or so, it's acquired an inner core. It acquired this by an interesting process. We're all used to freezing things and having them freeze at the top. But this isn't true for the Earth's core. It's cooled at the top because the Earth's cooling continually, but it's freezing from the bottom. And it may sound strange, but it's a question of what the melting point gradient is as compared with the adiabatic gradient, because the core is really, the interior of the Earth is very closely onto an adiabat. So maybe I'll get to the interesting question about what happens at this freezing surface. This is a freezing surface that is advancing at a rate of about 10 to the minus 11 meters per second. Okay, so that's the structure. Now this is the evidence that's come to light over the last decade. This is the length of day, LOD, in milliseconds. And as you can see, it's changing. And this is entirely due to forces within the Earth. Well, not entirely due. I mean, there's atmospheric and ocean circulations that have an effect. But the main effect is from the interior of the Earth. In fact, Raymond Hyde likes to say, if you took the circulation of the atmospheres of the oceans and you reversed them, you would not be able to explain such large changes in length of day. What's come to light recently is that there's a periodicity in this. Abaco del Rio, as his group, were the first people to discover this, and you can see the kind of periodicity. This is the derivative of the length of day. And here's another picture of it. And this actually translates the variation of length of day into the torque. This is a torque which the mantle is receiving from the core. You can see its periodicity. It's quantified about 6 years. It's not very regular. And the reason for this is partly because it's only recently there's been very accurate data. The data before 1960 was not adequate to see this. So this is the problem then. How are you going to explain these changes? And first of all, we make a gigantic simplification. We throw out all the talks of external origin. So that means we throw out precession, mutation, vibration, that they're all discarded. And if you do that, then the next talk, now let me explain my notation here, because it's a notation-filled subject. Well, I've got a hat on, something like that. That's the talk on the mantle. And when I've got a twiddle on it, it's a talk on the inner core. And there is a talk on the inner core, and part of the explanation of these phenomena lies in the inner core, because there's a coupling between the inner core and the mantle. I hope I'll get to that, but I'm not sure I will. As I said, it's got very big over the last 10 years. On the gamma with that, or the little hook on the top, that's the talk on the fluid core. So notice this notation. FOC means fluid outer core. SIC means solid inner core. And there they are. The angular momenta of these three things add up to a constant. And what are we looking at? We're looking at torques on the mantle which are approaching 10 to the 18th Newton meters. Let's see now. Yeah, okay. What are the four mechanisms that are available to change the angular state of the mantle? Well, here are the obvious candidates. Viscosity. Obviously, there's a friction between the fluid core and the mantle. Topography. That's because, in fact, the Earth is not spherically symmetric. I mean, the first approximation, you say the Earth is a spherically symmetric structure, but really it's a lie. It's not perfectly spherically symmetric by any means. And you have bumps on the core mantle boundary. And this introduced a subject which Keith Runcorn called geophrenology. Then you have gravitational field. Well, this is a newcomer. This has only been in the last 10 years due to Bruce Buffett, who pointed out that there's a surprisingly large gravitational coupling between the inner core and the mantle. And that last is the one we know and love, magnetic fields. And in this talk I shall concentrate on magnetic field stuff, although the other stuff is very interesting too, especially the gravitational and topographical connection. So, for example, if I'm looking at the mantle now, I've got these these are the four torques which make up the total torque on the mantle: viscosity, topography, gravitation, magnetic field. And more notation. CMB means core mantle boundary. ICB means inner core boundary. Okay. I hope it's okay. Stop me if there's any questions you'd like to ask. I think the notation. Here's the one about bumps. Here's the geophrenology bit. Here's the mantle with a bump on it, denoted by H hat. And curiously enough, the mantle imprints its topography onto the inner core. And this is because the surface of the inner core is a geopotential. Well, it would be in a non-turbulent core. Of course, the core is a very turbulent place. But if it was laminar and quiet, then all the equidensity, equitemperature surfaces would be equipotential surfaces, including this freezing surface on the inner core boundary. So Ri is the radius of the inner core, R0 is the radius of the core mantle boundary. Now, I think I won't get time to talk about this, but the fact that the mantle imprints onto the inner core, its topography, has this interesting consequence. Now, you must imagine that you're looking down from the North Pole onto the equator of the Earth. This is in the greatly exaggerated ellipse, and it represents the fact that one of the most important deviations from sphericity belongs to the 2-2 spherical harmonic, and this makes this slightly elliptical. Now, that imprints a similar ellipticity on the inner core, only by about 50 meters or something like that. It's enough. You get a deviation of that size, and you get a coupling between these two. This is a misalignment angle, phi. Actually, in the preferred minimum energy state, the bulges are aligned. Phi is equal to naught. But, turbulence is kicking this thing around all the time. So it actually deviates from this. Phi is not zero. What does that do? Well, you can imagine, this bit attracts that bit more than it attracts this bit. So this thing tends to oscillate. And this is relevant, because when you work out the time scale of this oscillation, by Jove, it's something like the time scale you're looking for. It's about something between 4 and 8 years, maybe. It's something you can compute fairly well, and it's in the right ballpark for understanding the data I showed you. But it's not the only explanation by any means. It's a rather complicated subject it's become. So I'm not going to talk about this unless I have extra time at the end, which of course I won't. So I'll go to the magnetic part now. Okay, so we don't want a very elaborate model. We don't want a model that has complications with, non-uniform density and that sort of thing. This is just the Boussinesq equations. So what are we dealing with here? Here are the Boussinesq equations. You assume that the density is constant, so div v is 0. And then you have these two inertial terms, and you have the Coriolis force, which is very important. You get gradient of reduced density, P over rho. Here you get the buoyancy, which really doesn't feature in what I'm going to talk about. C is what's called the co-density. That's because the core is driven not just by thermal buoyancy, it's also driven by compositional buoyancy. As the inner core freezes, it releases light components, which then floats upwards and stirs the core. So there's two parts to the buoyancy force, and they're combined together in this co-density factor. Then there's the Lorentz force, we know all about, and the viscosity, which doesn't play much of a role. I should have said that the four mechanisms I talked about originally, everybody had difficulty in believing that viscosity is an effective coupler of the mantle and core. Even turbulent viscosity is probably not enough. It's the main culprits for this talk are the other three mechanisms: topography, gravity, and magnetic fields. Then you have these equations, which you all know perfectly well. So I can move on, I think. Okay. Now, this stuff I'm talking to you now about has been known since the time of Moses. They're really very old stuff, this. The Rossby number is a measure of the inertial forces. It's a typical velocity divided by, well, we've got core radius and angular velocity here. And it's rather small for the scales of the radius of the Earth. And the Ekman number, which is that's based on a kinematic viscosity, not turbulent viscosity, 10 to the minus 15. But people who estimate the turbulent viscosity still say this is about 10 to the minus 9. So this is really a rather small parameter. Then the first thing you can do with this is to drop nearly everything from the equations I put on the last view graph. You just leave yourself with the Coriolis force and this range of pressure. An immediate consequence of this is the Proudman-Taylor theorem. You take the divergence of this and you get that the VdZ is equal to naught. You have to use div equals naught too. This says that the velocity does not change in the direction of the rotation axis. It's just a function of x, y, and t. Now, the simplest model of the core, we've taken to be spherical or axis symmetric or something like that. Then the velocity, to satisfy the boundary condition, you have to make the velocity just be in the zonal direction, in the phi direction, around the lines of latitude. So this means that this flow, let's think of the property of this flow. First of all, it depends only on s and t. S is the distance from the rotation axis. And that means that every cylinder, imagine, I'll show you a slide of cylinders in a minute, but every cylinder of radius s moves like a solid body in this this motion. Okay, well, that's a preliminary for the next thing. At the moment, that doesn't seem very relevant because obviously it's not right to drop everything like this. But let's go to the oh yes, here it is again. Here is a depiction of the cylinders. Here's a cylinder of radius c. It's all moving together with its own velocity about the polar axis. Now that's what it is if you're outside the inner core. If you're inside, the situation is more complicated. You have two Taylor cylinders, one above and another one below, which is not shown. But again, the motion is only dependent on s and t. Am I going too fast? No? Okay, that's good to know. And one of the nice properties of this motion is that it has all the angular momentum in the core. Every other part of the motion has no angular momentum. And so you can test this. This was done by Joe and Lemuel and a student here. And this is kind of verification of this idea that the angular momentum is contained in the geostrophic motion. You see, what did they do? First of all, obviously you've got the length of day data available, and from the length of day data you have information about what the angular momentum of the core is doing. Second, you can infer the angular velocity of the surface of the core. You do that by extrapolating down from the Earth's surface to the core surface. You extrapolate the magnetic field and you get the idea that what the surface motion is, and you extract the part belonging to the zonal motion along lines of latitude, and from that you get some idea about what each cylinder is doing, because we've seen each cylinder's independent entity. So if you see what it's doing at the surface, then you get some idea about what its angular momentum is. So what this verifies is that these things are rather well correlated. Now, if you go back to 1825, there's lots of observations here, but they were low quality really. Only recently they've got high quality data. The high quality data certainly indicates that there's some correlation between the dotted line, which is one of these things. Oh yeah, this is the dotted line is the length of day information, and the other one is to do with core surface motion. So this indicates, I think, that you're on the right track. But let's get back to reality in the sense that the geostrophic equations are too simple. It's not, motion isn't as simple as that. The motion is often represented by this approximation called magnetostrophy or magnetogeostrophy. Let's look at these equations. And I only boxed the last one because that's a modification of the equation of motion I showed you before. You can see the inertial forces have been dropped entirely. There's only the Coriolis force left. But the right-hand side, you've only dropped the viscosity as being too small. You've kept everything else. There's the buoyancy, pressure, and Lorentz force, and so on. And long ago, I'll come to that. Yeah. The interesting thing about this is that since you've dropped the inertial forces, there are no Alfvén waves. The Alfvén waves went out of the window at the same time as you dropped the inertial terms. This means that the wave motions are really rather different, and they're very slow. Coriolis forces slow up the time scales enormously. The time scale here has got Tm, that's M stands for Mach or magnetic. It's this time scale. And what are the symbols here? VA is the Alfvén velocity, L is the typical length, and tau eta, that's the free decay time. That is, if you just shut off the dynamo, it's the time the field will take to decay, and it's something like between 10,000 and 100,000 years, very long time scale. Lambda is the Alsace number, which I introduced on Monday. It's defined over here. No, it isn't. Oh, there it is, defined over there. This is an enormously long time, and this is crucial for what's coming. Okay, so J.B. Taylor, plasma physics fame, he looked at these equations and he noticed an interesting property of them. Now, we'll write the velocity in this form, velocity, and so far you can add any zonal motion to it. You've got, so far you've got no way of determining the zonal motion. This geostrophic motion I introduced before. But Taylor showed that the phi components of the Lorentz force, if averaged over these cylinders, that's what these double brackets mean. This means average over each cylinder that we had in that previous picture. It is defined mathematically as a cylinder outside the inner core. He showed that this was zero. Now, the proof of this is very simple. It just means that it's all about conservation of mass. I assume it would work for the sun as well if you made allowance for the fact that the density is varying with position. But in the Earth, it's a good enough approximation to take this uniform density approximation. So here you have this remarkable result. What is the consequences? Well, J.B. Taylor noticed that this is, first of all, restrictive. If you say to yourself, I'll put a field in which satisfies this, it's very hard to find a field which satisfies this condition, actually. What he showed was that if you assumed that it was satisfied at a certain time, then you could say that the system might evolve in such a way as to preserve this. Now, what does that mean? It means that the time derivative of this must be zero. Not only zero initially, zero for all time. So he followed up what happens if you say the time derivative of this is 0. And what you get out of that is a simple second order equation, and it's got a nice property that if you assign the angular momentum of the system, then it has a unique solution. So where are we now? We've now determined the, or he's determined in principle this Vt. Up to this moment we didn't know what that was. We now know what the zonal motion is, and of course it's satisfying its geostrophic equation, magneto-geostrophic equations, so it's slowly varying. Now that's an important point, it's slowly varying. And never mind this junk out here, I just put that in for completeness. So isn't this remarkable? Because it's now a difficulty. Okay, J cross B, 3 components, average should be 0, but anybody can say to themselves, I won't accept that, I'll just put in a current. And if you put an arbitrary current into the system, then it won't satisfy this condition. There's not a chance it will satisfy this condition. So, in a sense, something's gone wrong, in some sense. And what's gone wrong is quite an interesting story, really. Obviously, what's oversimplified. So magnetostrophic equations, in some sense, are too simple. We've thrown out something we shouldn't have thrown out, because otherwise I would be in this awkward position of having an obvious contradiction of J cross B being 0. Obviously, we should restore some terms, and the obvious term to restore is the inertial force. So you go back to this equation we had before, and you say, I made a mistake when I threw out these terms here, I should do something about them. And the obvious one to restore is this dV dt. And that has an enormous effect, because it reintroduces the Alfvén time scale. So all of a sudden you've got your Alfvén wave back again. And they're very fast. I've got something here about, I'll put it. Well, sorry, I'm going too fast there. I'll come to that in a minute. But you restore that term, and you get this easiest level. This is the replacement of Taylor's condition. Taylor's condition was right-hand side equals 0. Here's the effect of the inertial terms, and you massage the equations, and what you get out? You get out a wave equation. There it is. It's a wave equation in S and T with some obnoxious term which doesn't really enter the discussion here, but you see this is a wave equation. Okay, it's got complicated coefficients, sure. You see the Alfvén velocity coming in there. If you ignore that junk, S squared AS, this is A is the area of the cylinder, and S is, as I said, distance from the axis. This thing is obviously a wave equation. Throw away the junk and just keep the A squared, and you see it's a wave equation in the S direction. So this system is now propagating waves in the S direction. These are the torsional waves. Here they are again. See, the cylinders are now rotating, not counter-rotating here. They're twisting, zonally. There they are, bending a line of force. Now you remember your elementary magnetohydrodynamics. You bend a line of force, it exerts a tension. Its tension pulls the bits together, and it promotes a wave, and there you've got a wave going in and out from the inner core. Okay, and this is the thing I want you to drive home at this stage, that there are 2 time scales, and they're very, very different. You've got this magnetostrophic time scale that I introduced with the magnetostrophic approximation, of the order of 10 to the 4th years. And you've got this torsional wave time scale, the time it takes the torsional wave to cross the core. It's about 5 years maybe. No, nobody knows precisely, but this is rough order of magnitude. Okay, so now we've got some further complications I should try to explain here. Let me just go back a minute to this equation. This is torsion away, but it doesn't satisfy the right boundary conditions. You should satisfy here no slip condition. For a solar application it wouldn't be no slip, of course, it would be probably zero stress or something. And here you also have to satisfy magnetic boundary conditions, and they're not satisfied. You have to match the field here to a potential field in the mantle. The mantle is a poor conductor of electricity, so essentially it's coupled. It's coupled to a potential field, more or less. And so things have gone badly wrong at the boundary, and that means that you should satisfy these conditions. Now this is the no-slip condition. This is the zeta hat is the angular velocity of the mantle, and this condition isn't important because the magnetic Prandtl number in the core is extremely small, like 10 to the minus 6. These are the important conditions, the magnetic conditions. And these say that the horizontal components, that's a capital H, of the electric and magnetic field must be continuous with those in the mantle, in the mantle. But they don't satisfy this. Now let's think about what you all know, I'm sure, the skin effect. How is this relevant? Well, first of all, what is a skin effect? You remember you're a solid conductor, you oscillate the magnetic field, and this penetrates into this solid conductor, and there's a certain E-folding distance, the magnetic diffusion length, and it's negated, it's wiped out, this field, in a distance proportional to sigma mu to the half. Sigma the conductivity, mu the permeability. So it's wiped out in a very short distance. Now how is this relevant to my theme here? Well, you see, these cylinders are really providing the oscillation. They're all threaded by magnetic fields, and as they oscillate, they produce an oscillating field at the boundary here, and that oscillating field penetrates into the mantle, and the mantle is actually weakly conducting. It penetrates into the mantle, and it provides currents flow into the mantle, and the currents create a Lorentz force, and this is the magnetic coupling between the core and the mantle. So this is how the skin effect is relevant. The skin is only very thin, about 10 kilometers. So you've got then a magnetic diffusion layer, I call it. Now, people who are expert in magnetohydrodynamics will know that there's a thing called the Ekman-Hartmann layer. And this is a kind of weakened form of the Ekman-Hartmann layer. As I mentioned, the magnetic Prandtl number is very small, and so it doesn't really resemble the Ekman-Hartmann layer very closely. It's really a magnetic diffusion layer. Here it is, thickness d eta, and a very, very thin Ekman layer, which is probably as thick as that line up here. Now here's one of these cylinders meeting the core mantle boundary, and because of the failure of the solutions to satisfy the boundary conditions, you get some interesting phenomena. You get, for example, that there's a leakage current. The leakage current is a jet of current comes up here into this region and then moves almost horizontally. Some of it goes into the mantle, but it's mostly shot along the interface. And also, interestingly enough, there's also a magnetic part, a momentum part to this. This represents momentum, rho v. Also coming into this boundary layer and shooting out in this direction, and also actually rotating about the axis. And these have a significant effect on the coupling. And that's really a pain. It means that more work should be done in this area than I've done on it so far. But the effect of this is quite strong. I started off with this equation, except for that K. Now this K is what the boundary layer produces. You saw the rest on the previous view graph. And if you take the essence of this equation and transform it, you find that what you get is a damping term. So here's these two basic parts again, plus this damping term. And this damping term is of a form, I think, that nobody's noticed before, that actually well, I should back up a minute. People say that the coupling is due to the conductivity of the mantle. That makes sense. And they also say that the mantle is the main reason why the torsional waves are killed. Because obviously, if you're sending energy into the mantle from the wave is going to attenuate. But actually, the boundary layer that I mentioned on the core surface also contributes. You get, this is the one for the mantle with a hat on it, this is the one from the fluid core, and this has an extraordinarily, can have an extraordinarily big effect on the solutions. It can dampen them more strongly, depending on parameter values. So, we get to the, you can compute the axial torque on the mantle, and angular momentum is conserved and all that sort of stuff. And let's look at the effect of the ohmic losses, taking a simple version of this. Here's the alpha transmission time across the core, and you find this is the damping effect. This is the couple on the mantle, axial couple, and it's proportional to the difference in angular velocities of the core. It's a simple model in which the core is rotating together. And here's the angular momentum of the mantle. And this is a damping term. And it's rather big. And there's a kind of paradox that arises here. That the coupling, you want if you believe that the magnetic field is the main thing providing the coupling of the mantle of the core, and a lot of people believe this, then you've got to say to yourself, the damping must not be so strong that the wave is damped before it can cross the core. It mustn't be over-damped, in other words. And this turns out to be a rather delicate balance, or seems to be. The values I've given here, the wave e-folding time of the wave disappearing is 60 years about, whereas the wave of descent crosses in 6 years. But unfortunately, these values I've taken do not produce a torque of 10 to the 18 Newton meter, which is our target torque. That was what we were aiming for. It produced something like 10 to the 17 or 10 to the 16, something rather smaller. So you say, oh, never mind, we just up the mantle conductivity, all will be well. But it isn't, because what happens if you up the mantle conductivity? You up the dissipation. So at the same time as you increase the torque between the mantle and core, you also increase the damping. So you're in danger of killing the wave before it can cross the core. How am I doing on time?
Okay, 15 minutes.
15? Oh, wow. Well, I don't know if you're all bored with this or not. The thing about this, this is, we call it the magnetic coupling paradox. And perhaps I should say that nobody knows the numbers closely enough to say whether this paradox is a problem or not, but clearly it's a potential problem with this sort of stuff. Well, I thought, when I prepared this talk, I thought I was going to give you far too much stuff, so I cut the end of it out, but I left it at the end just in case I wanted it. So I'll go back, if you forgive me, to an issue which, or I should say this too, there's one other issue, that is the fluid, the waves couple, or the fluid core is tightly coupled to the inner core on these time scales, but I won't go into that. I'll go to this other topic. I'll go back to this topic, which I mentioned before. This is an interesting topic of gravitational coupling. And it all depends on how non-spherical the Earth is. And so let's review the reasons why the Earth is non-spherical. The main reasons. You can identify 3 reasons for this. The first reason is a simple one. You know, we all know the Earth is like an orange, flattened at the poles. Well, the core is like that too. It's also flattened because of the Earth's rotation. And the parameter which determines that is this parameter of gravity. And it's about 10 to the minus 3. But this one is not relevant to this question of length of day. It is relevant to things like precession, nutation, that sort of thing, but it's not relevant to us. It's the asymmetric ones, the ones depending on phi. And this is the main one. There's general agreement that this is the main deviation of this is phi is the gravitational potential, and this is the deviation from sphericity in that gravitational potential. The gravitational potential surfaces are not spheres, and they're sort of where this thing's constant. Okay, so corresponding to this, we can define a parameter which is defined here. The dashes here refer to deviations caused by mantle. These gravitational anomalies, why do they exist? Well, it's because the mantle is more or less immobile. It has a viscosity of something like 10 to the 19 poise or something. It doesn't move much. So if there's any deviation in density, the flow to correct that it takes a terribly long time. In other words, the mantle is not in hydrostatic equilibrium. And that's what this term represents. So in corresponding to that, you have this parameter, which is rather small than that one. But this is a very important parameter, it's epsilon A, because this is responsible for all I'm going to talk about. Also, convection. Obviously, there are density variations connected with convection, but these are even smaller. They're like 10 to the minus 8, 10 to the minus 7, this typical parameter. So we forget about those. We'll just concentrate on this one, because that does have an effect. Okay, so we now look, first of all, at the topographic torque. Topographic torque is by bumps. Bumps create pressure differences on the surface of the inner core and on the mantle, core mantle boundary. There's the pressure. The normal is not parallel to the radius vector, therefore this quantity is not zero, and it contributes to this torque. Okay, so that's one reason for anomalies. Let's go to the gravitational torque. Now this is interesting too, I think, because it's not generally recognised that the when you do gravity, you don't have to always use the volumetric force. All your integrals can be converted into surface integrals. I discovered this when I read an ancient book on magnetism by James Jeans. And in this book he has the torque exerted in electrostatics by distribution of charge. Well, of course, gravity is just the same, because all you do is reverse the sign. Gravity is governed by exactly the same theory as electrostatics, except for that sign change. So you can convert all these integrals into surface integrals, and here's the gravitational torque on the mantle, this one, and you add the two together, you find a remarkable thing, that the two together wipe out the effect of the fluid core. That's because the fluid core responds to gravitational, well, it's in hydrostatic balance. So, what's the state of affairs? You have this G plus T torque, that's gravity plus topographic torque, and these adiabatic parts of these things necessarily satisfy this balance. That it says that the torque on the mantle created by the inner core is equal and opposite to the torque created by the inner core on the mantle. And you can say more than that, because the Earth is always trying to get to its minimum energy state. So when we had that oscillation I showed you before, the Earth always tries to get to its minimum energy state, and that's why there's this oscillation. It's an oscillation about a minimum energy state. Okay, there it is again. It's always trying to get back to phi equals naught. Okay, now I've just got two more view graphs, I think. This is one of them. Here I've got that, I returned to that, which I had before. This is the main deviation in the gravitational potential of this form. And remember that I said before, the inner core boundary is a geopotential. It's a freezing surface, it's a geopotential. That means you can work out the shape. You know this is what the mantle is producing, and you can work out the shape of the core, assuming everything's quiescent and non-turbulence and all the rest of it. You just say to yourself, I want this phi, which is the sum of these two, the spherical potential of the Earth, the main, gigantic contribution here, and a very small contribution here. So you essentially do a perturbation analysis. You just work out what the height of the bumps that are produced. And that's, to make this equation satisfied, to make constant potential on the inner core surface, you have to have bumps on the inner core boundary, and this is the height of the bumps, about 50 metres. And you might say, well, 50 metres is nothing, surely that can't do anything. But in fact, it's quite important. Buffett was very smart to notice this, that it's, you can work out the torque now. You've now got your bumpy inner core, you've got your mantle, and you can work out the torque between them in a very precise way. Here it is. It depends on this angle. That's the misalignment angle again. So it goes to zero when you're in equilibrium, and when you deviate from equilibrium, you get this restoring torque. Magnitude is given very precisely by that, where that's the excitation, and this A twiddle is the response, which I've just indicated. So you have two coupled equations for these, the angular motion of these two. Very simple theory, and you can work out what this frequency of oscillation is. And it's, oh God, yes, there we are. Here you get 4.1 plus or minus or plus, because there's that's another story. 4.1 plus or minus about 2 years. So it's really a tight, quite a tight oscillation. So that's more or less it. The whole subject has got very complicated indeed, because you can see that there's time scales which are very similar to each other. There's this one which I've just touched on, this one of 4 years. It's not the only one. You've got that wave going across the core. It's going across in comparable time, 6 years or something. There's all these interrelations of these different effects. And I think this subject is going to undergo quite a rapid development in the next few years. This is really the end. Yeah. Thanks.
questions.
Oh dear.
Recently there has been some work by Emmanuel Dormy,
Yes,
Balbus and Petit de Monge on not on torsional oscillation but on so-called geostrophic magnetorotational instability, which is also a sort of wave which is running along the tangential cylinder, which can also be a candidate to transfer angular momentum in a way. It's the same time scale, it's also the alphenic time scale, so it could be interesting to check if, or how does it relate to your model?
Well, I don't think, as I say, it doesn't particularly affect the angular momentum, but the time scales would be interesting.
I think it's the same, it's alphenic time scale.
Alphenic time, okay. I'm sorry, I don't really know about that. I keep on finding things I should know about and don't. It just I don't do enough reading.
If turbulent viscosity exists, what's the typical time of turbulent viscosity processes?
Time scale. Oh gosh. Well, it changes the viscosity by about, well, the kinematic viscosity, it changes it by about, maybe 4 or 5 orders of magnitude. This is what people estimate after the turbulent viscosity, but I don't know what that corresponds to the time scale. It's a big effect, this turbulent viscosity.
It could be possible that this effect simply destroyed totally torsional oscillation. I've read all the time about it.
About what?
Yeah.
Well, everybody in this business have made estimates, and a few people still think that viscosity, turbulent viscosity, can produce interesting effects. There are a lot of things which act against it, not just the turbulent viscosity doesn't seem to be perhaps big enough, but also there's maybe a stratified layer at the top of the core. Now, that will decrease the momentum transfer, clearly. And so I suspect that the viscous and turbulent viscous effects are not important, but some people would disagree. A minority, I would say, but yeah.
Because there is this very strong cutoff of all this process, about half year or something, 1 year in all this stuff.
Well, it's very difficult to get information on a short time scales because they're cut off by the mantle. You can't really get any information.
I have a small question. Do we know what is the Young modulus?
What?
The Young modulus of the core mantle to estimate the importance of this?
Oh, these gravitational effects, you mean? First of all, there seems to be agreement that it's this n equals 2, m equals 2 is the most important deviation, but the estimates of the constant involved, the expense of the potential, they differ by about a factor of 2. And that's why the estimates I gave at the end here had plus or minus 2 years, because I spread it over the available data. And so they're rather uncertain, but there's, I think, agreement that it's the 2-2 gravity anomaly is most important. That's the impression I get. I'm not in that business, but I read what I...
I have a question, Paul. You had your bumps on the scale of 50 metres.
Yeah.
How does that scale compare with the scale of the boundary layers that you were talking about?
Very much smaller.
Very much smaller.
Yeah, the boundary layers are about 10 kilometres, I would say. Yeah, they're very much smaller. That's a good point, actually. Yeah.
Do we have any other questions? In that case, let's thank Paul again.
Thank you very much.
Our next talk is from Professor Sokoloff. He's going to talk about alpha fluctuations and a simple model of geomagnetic inversions.
So, the problem which I would like to address is the following. This is a well-known in geology geomagnetic time scale. So the sequence of epoch in which Earth's magnetic dipole was parallel to the contemporary one and anti-parallel. And here it is a time shown in millions of years, and these black and white strips indicate various epochs. So what we, apart from any kind of geological information, what we can learn from this, it is a long-term dynamics. And if we accept that the time of inversion is somehow related to the dynamo time scale, the time of in which dynamo is able to modify substantially magnetic field, you learn from here that this time scale of this geological time scale is much larger than the dynamo time. The question is what we observe here, some new dynamics, what is beyond somehow traditional concept of alpha omega dynamo or whatever else, or it can be somehow embedded in traditional concept of dynamo theory. Look now on the plot concerning solar activity. Again, there are 11-year oscillation solar cycle. Okay, we agree that it is somehow related to the alpha omega dynamo or maybe some other kind of dynamo, but here there is a Maunder minimum, and again the time scale of one solar cycle and time scale of Maunder minimum and the time scale between such grand minima we know from say isotopic data that there was several such events. There are different times, and so again the question is this dynamics more or less related to the traditional ideas of dynamo theory, or there is something new. I fully appreciate that both phenomena, geomagnetic reversals and grand minima of solar activity, can be obtained in numerical simulation, in mean field dynamo simulation, or in direct numerical simulation. So the known ideas can reproduce it, but I fully agree with Eugene Parker, who said that we have to explain it somehow. It is not enough to reproduce it in numerical simulation. We have to elaborate some language, some concepts which help to explain what is really going on. And for example, for geology, it is they are not very interested in details of dynamo theory, how it works in details. They asked, guys, please say, is it something what happens with flows, or it is something magnetic, or some maybe superplump or things like that? Please address this topic. And I think that we have to elaborate some simple, very simple model, which of course don't pretend to replace numerical simulation, but can help to explain what is really going on. And my aim is to present here one of such simple model. I am completely not sure that this is the most adequate to the nature, but at least it can somehow help to understand. So the suggestion, I am starting from the idea that it is something what happens in magnetic systems. So it is more or less standard word of dynamo concept, but with some modification. Of course, I don't object in principle that it could be something what happens with hydrodynamics, but I try to explain it staying in the framework of dynamo theories. Then I accept that there are some internal relation between geodynamo and solar dynamo. It is something what happens in spherical and below, and maybe the parameters are different, but it is more or less something what exploit differential rotation and alpha effect. Okay, and then, but of course I need to introduce, and in addition, I know very well that geomagnetic in geodynamo one can modify flows substantially by magnetic forces, but just now I would try to explain inversions having very simple mechanism of saturation. So I will accept that it is simply a simple alpha quenching. So what have I introduced to get long-term dynamics? It was an old idea of Peter Hoying that fluctuations of alpha can help. Hoying published several papers of this direction, and we exploit here his ideas with some modifications which looks for me very minor, but Hoying suggested it about 20 years ago, and that time people don't anticipate some details. I would not like to go in these fine details what Hoying did not took into account. But as a result, we need something about 10-20% of fluctuation of alpha. There are long-term fluctuations. On the time scales comparable with solar cycle or dynamo times in geodynamo. Then the idea, and then something more what I needed is a competition of mode. I explain it further. So earlier we tried this idea for solar activity. There was several papers published by Ilya Usoskin, David Moss, Valery Totuvarin, and myself. There is a analysis what happens if we get alpha fluctuations to simple Parker dynamo with simple non-linearity. It is what it produces. You have something like normal cycles, and then system went from time to grand minima. There is an event of when a grand minima starts, and here you can obtain asymmetric butterfly diagrams and things like known in solar activity studies. I don't concentrate attention on this. I just make a statement that it works for solar activity. First, what about geodynamo, Eugene Parker somehow didn't pay attention, didn't suggest that such a nice model as Parker migratory dynamo for the Sun, something similar for geodynamo. Here I try to get something known for something familiar for the word of geodynamo. Here I know there is a Rikitaki dynamo, but it is quite artificial. And I try to take for this Rikitaki dynamo that it is just a dynamical system. And I would like to obtain from Parker migratory dynamo something like this finite dimensional system. And it is possible to do like that, so some more figures about this solar activity. And so I suppose that basically it is the same Parker dynamo, so bipoloidal is transformed to be toroidal by differential rotation, and inverse transformation is performed by alpha effect. And then I take the equation of this dynamo and make a projection of this equation of several first free decay modes. And I see how many modes we need to make this dynamo active. It is an old idea of Karl-Heinz Redler, which he exploited with Frau Wiedemann, as far as I remember. And a novelty here is that that time you had difficulties that the series are very low convergent, and we try to just to analyze which terms are useless and throw them out. And so it is not a very good way to obtain numerical scheme, but as a way to get such low dimensional models, it is perfect. So after some algebra, we arrive that to the following conclusion. It is quite a lot of algebra, but still. So looking on this scheme, you may and if one naively understand this BP as one free decay mode and BT as the other free decay mode, then the machine doesn't work. The minimal number of modes is 3. But then you get you lost a mode which is responsible for magnetic moment. And because I somehow know that the geomagnetic field has a magnetic moment which is directly observable, we add this mode as well. It helps very much to and makes the excitation threshold much lower. And as a result, we obtain the following set of 4 ordinary differential equations. Here, R alpha and R omega is well known dimensionless numbers. A1, A2 are 2 poloidal modes. A1 is responsible for magnetic moment, and later I will give plots for this A1, and B1 and B2 are 2 toroidal modes. Psi is a parameter which is responsible for nonlinear saturation. You can include it in magnetic field and measure the magnetic field in equipartition field strength. So psi is responsible for equipartition field strength. And what is important here is that if you excitation diagram is indeed controlled by a product of R alpha times R omega, but just for illustration it is easier to make 2D plot. There are hyperbolic curves in the lines indeed. So here, if the excitation is very low, you have just decay. Here you have oscillations. Of course, if you have very oscillatory solution, of course, if you take a very large dynamo number, your simple model becomes inadequate and it works bad. I don't go to this region. What is more important, here you have an area of steady growing solution, which is stabilized to steady solution. And here you have an area of something what people who works on here you have something like what is known as oscillations. So oscillations with non-zero mean. And here something what people who worked on VKS experiment are referred as dynamo bursts. So the plots are like that. Oscillations it is clear, oscillations it is something like that, and dynamo burst is something like that. Something like that. And what is, I'm sorry, and what is important that here, steady solution it is clear, and between oscillations and these oscillations and dynamo bursts, there is a region where field decay. This excitation is much less effective than that one, but this still exists. And what happens then? If you enlarge your alpha, you moves from this area of oscillations to the area of dynamo burst. And this you can switch the polarity of magnetic field. And then you return back. If you go from here to there, you obtain a long epoch without field repulse. It is superchron in geological terminology. Moreover, here you see that if sometimes you went in the area in which a reversal, a dynamo burst occurs, sometimes you obtain just reduction of magnetic field intensity without reversals. It is a well-known phenomena named excursion in geomagnetic studies. The point is that this stage is quite, this period is quite long, and if you arrive there at that time, you obtain excursion, and only if you arrive at this stage, you obtain very rapid inversion. And the inversion itself occupies much less time than the period of this between this dynamo bursts. So it is all these phenomena are known, say, from VKS experiment, but of course the particular dynamics there is different. But people from who thought about VKS experiment suggested simple finite dimensional scheme to explain VKS experiment as well. I like them very much, and it was an impulse for us to think about geodynamo. So, and then of course we try to simulate something like artificial geomagnetic time scale. We simulated as many reversals as there was there is geomagnetic time scale is well elaborated for the first 160 billions of years. We calculated how many reversals there is in corresponding geological table and simulated as many reversals and then identified the length of this. We worked in arbitrary time unit. Really we obtained something more or less similar to the real time scale. It is, I stress again that the basic idea was suggested by Peter Cohen, who explained that it should work, but it is some realization of Cohen's idea in modern context. He realizing his idea, he made some suggestions which looks not completely adequate nowadays, but in principle the idea works and leads to results which look reasonable for me. We didn't try to fit the results with observations in details, but of course you see there is something like clustering, or you can for example here there are clusters of rapid reversals and so on, but such a fitting to the observational data, to geological data, requires some work with geologists first, and second, we need to make this model not so dramatically oversimplified. Here we try to remove everything what is not ultimately required to obtain such a picture. Of course, it is more than possible to include influence on differential rotation, conservation of alpha, or you can add shell model, everything what you want. And for example, here there are very interesting ideas of Graham-Sars on how to add shell model, everything like that helps, of course, but even in drastically oversimplified situation, alpha fluctuations are sufficient to mimic reality, at least in zeros approximation. Thank you very much indeed.
We have time for questions.
When you derive these four equations, what kind of assumptions do you use for statistics of fluctuations of alpha? Do you perform any averaging?
No, so we took standard Parker migratory dynamo equations,
linear equations,
then add simplest nonlinearity, and then introduced just by hands fluctuation of alpha. What about fluctuation of alpha? There is again very simple. We divided time axis in units of of constant length, and say that alpha keep the spatial distribution, and what is fluctuating is the amplitude of alpha. It is abruptly changed, like Orwell explained about this model with prompt losses of memory. In Orwell's book, memory is lost every midnight, and we lost memory at the end of this interval, nothing more.
And you introduced, you said simple nonlinearity. Do the nonlinear alpha or just...
Just nonlinear, just simple alpha plane.
Alpha plane.
Yes, it is no problem to introduce something more, conservation of helicity or whatever else, but we try to keep with most straightforward ideas.
Maybe one little remark. I think the problem with these low-dimensional models is sometimes that you get completely the wrong asymmetry of the reversal. So you know in the geodynamo reversals you have a very slow decay and a very fast recovery. And it's well known that the Huygens model has exactly the opposite behavior. So what I believe is, and it has also described by the French guys you mentioned, as a settle node bifurcation, but I believe that the spectral background of the settle node bifurcation is simply that two nodes are coming together, coalescing at some exceptional point, forming an oscillatory branch, and this explains all the features, including the asymmetry of the reversal, for which you need a negative slope of the growth rate in the spectrum. So I think one should be a little bit careful with the too simplified low-dimensional models.
I fully agree. Of course, it would be strange to insist that we can explain everything on such simple level. I forget one important detail. There are 4 authors of this paper. It was the first time in my life when I was invited to the director of our department, and he said to me, please don't work on such very theoretical issues. Please concentrate on this problem and suggest something simple and understandable for people working in geomagnetism. He is an expert in geomagnetism. Then he gave me a good student, and he and his one of his team helped us to organize all this stuff. There are two members from administration. It is the first time in my life when administration take care of what I am doing in science.
Short comment. You know, if you just take into account magnetic helicity in this situation, possible chaotic behavior. Maybe you demonstrated many years ago with Alexander. So if it will be 2 mechanisms together, I think it's not so trivial.
Of course, it is plenty of possibilities to include more in all this stuff. Of course, we planned. I didn't focus the attention on various gaps which we have in our analysis. We didn't consider competition between dipole and models of dipole and quadrupole symmetry. It is half a sphere only. So various things have to be added. And what was important for us is that the phenomena can be obtained in extremely simple situation.
Axel?
Your model does have shear, right?
Yes.
Yes, and did you also consider models with zero averaged alpha?
No. No. We used basic alpha and 10-20% fluctuations around it. So
the time scale of reversals, how does that relate? I mean, you do have no time scale, I suppose. At least not in the geo record. But in the model, you might still have a time scale. And would that be connected with the turbulent diffusion time scale?
So the time which the system needs to reverse is several times smaller than the dynamo time scale, than the time dependent on growth rate. Look, it is visible on this here. It is visible. What is required for reversal is Z, and the dynamo time scale is. So it is the reversals is really very short time phenomenon.
Okay, final questions.
So together with Peter Hoying, we tried in the past to compare amplitude approaches with direct numerical simulations. And one fundamental problem which occurs is that reversals in direct numerical simulations occur in a dynamo regime where all kinematic approaches break down. Just a comment.
Okay, well, I'm not bombshell. I think it's time for us to go for lunch. Do you have anything to announce, Axel? Or? No. Okay.
Any questions about something that I could announce?
You mentioned that there is a reprint of the Krause-Rädler book available, and that there's a web link. Maybe you can send that to all the conference participants.
Show you that link. Mr. K, just Google MCAR website. But